All right, so then we get into count dependent variables. And again, it may look a little unfamiliar, but you can do it. We're going to talk about the basic model here, Poisson. So you get to use all these wonderful terms now. And it talks about probabilities. You remember the picture that I showed you on the first slide? A high bar for 0 and then dropping off very rapidly. That's well described by something that looks very funny here. But if you look at it long enough, it'll tell you that you have one parameter, mu, that's a parameter, mu, and then the rest of it is either r, which is the number of times you did something, so that's the count itself, r here and r there. And then it's e to the power of, we're familiar with e, you know, e to the power of something. You can do that in your little hand calculator. So u varies from 0, 1, and up. Y, mu is the mean, or referred to as the rate. And this r exclamation point means r factorial. So as it says, it's 3 exclamation point is 1 times 2 times 3 equals 6. And we have to remember that r equals 0 gives the value 1. R equals 0 meaning not having done something in the last month. So that's a very important point. So when r equals 0, this becomes 1 down here. Mu to the power of r is then anything to the power of 0 is 1, right? Anything to the power of 0 is 1. So you end up with only e to the power of minus mu. E to the power of minus mu is the probability for having the count 0. Am I speaking too fast? Too slowly, I guess. All right, so now that's the probability, but now we want to do a regression. We want to relate this probability to x. So we use a linear regression, but it's linear only for the log of the rate. So log of mu is now linear, just like logit was linear. So statisticians, they make they focus on a parameter or a function of a parameter that makes the right-hand side linear. That is, it's not x to the power of 2, well, it could be, or it's not e to the power of x, rather, or something like that. And then, given that that's log of mu, if you take e to the power of that, it becomes mu. And on the right-hand side, we have e to the power of beta 1, which is the change in the rate mean of u for a unit change in x. So that's one way of interpreting the coefficient. But you could just go with sign and significance for beta 1 to understand things. Now, the Poisson model can be extended to have a random intercept. And you write this then first as the linear equation that we had before, plus a residual, which can capture unobserved heterogeneity, just like regular linear regression. And that can be assumed to be normally distributed. And you can look alternatively at this, as we will do a couple of times today, as having a random intercept. So when you have a coefficient parameter, rather, that has a subscript I, that means it varies randomly, meaning that it varies across individuals. So this is not a fixed coefficient, it varies across individuals, just like in multi-level modeling. So, and then you describe that variation. The mean of that is beta 0, but then you also have a residual, a random part to it. If you express it like 6, the residual can be viewed as a continuous latent variable measured by the dependent variable log mu, where the variance is an additional parameter to be estimated. All right, that's one Poisson version. A more important Poisson version is the zero-inflated Poisson. It tries to avoid the limitation of Poisson that assumes that the mean and the variance and the mean are the same. It's one parameter, and it's both the mean and the variance. But very often in reality, you have variances much greater than the mean because of a high floor effect, preponderance of zeros. So take an example. In alcohol research, a common question format is how many times in the last 30 days did you drink 5 or more drinks at one occasion? The majority answered 0. Now we want to think about that. 2 reasons for the answer 0. Some subjects may be non-drinkers, and some subjects may be drinkers but have not engaged in heavy drinking during that period. So if you observe 0, it could be for 2 different reasons. We think of that as a mixture of two subpopulations or two latent classes. Those who don't engage in that because they don't drink, and those who happen to not binge drink but actually do drink. Now, we don't know who's who by observing a zero, but by fancy statistical modeling, we can tease it out. So a mixture is really something, has to do with latent classes, that is unobserved group membership. And we're going to try to, by analysis, figure out who's in which group. All right. Now, if you accept that, then let's think of pi here as the probability of being in the zero class, being a non-drinker, and then 1 minus pi, the complement, is the probability of being in the class that follows a Poisson model where zero counts as well as positive counts can be observed, right? So 1 minus pi is the probability of being in a class that follows the regular Poisson model where zero is allowed. So these are the drinkers, but they can have zero binge drinking in the last 30 days. And then you write the probability as a mixture being then a sum of two parts, probability of being a non-drinker plus the probability of being a drinker but drinking zero, doing zero binge drinking in the last 30 days. And here is the zero count part that I mentioned before. You know, when the count R in that picture is zero, the Poisson model simplifies to this expression. So you have probability of being a drinker plus probability of not being a drinker and drinking, but not binge drinking in the last 30 days. So that kind of mixture is the hallmark of ZIP modeling, zero inflated modeling. And that kind of zero inflation, that is, that extra class of non-drinkers, that thinking comes back in several shapes and forms as we go on to other models. Now, in this ZIP model, you actually then have two parts to the model. Not only do you have the rate equation here, but you have the logit model. And here you see one of those three forms that I talk about. So this is the logistic regression here in the second alternative that I mentioned. So we logit for the probability is linear in X like this. That's the probability of being in the zero class. And then you have the usual Poisson rate model here. And the interesting thing is that you don't have to have the same slope. Gamma 1, this is gamma 1, is not necessarily the same as beta 1. So a certain X variable can have different influence on the probability of being a non-drinker compared to how much they drink if they are a drinker. So that's very useful, very flexible modeling here. Whoops, I'm going to confuse these two. A very flexible modeling you can learn much more about your data by having two slopes from these two equations due to the zero inflated model. And the mean is then a little bit different than mu, is the mu times 1 minus pi. And you may want to circle this bullet, second to the last bullet here. If the logit gets large negative value, it implies that zero probability of pi for being in zero class, and the inflation part is not needed. That happens quite often in the examples that we see at Mplus support. Negative binomial model is another count model, very popular and perhaps better than even ZIP, zero inflated Poisson. It's expressed like this: linear regression plus a residual picking up unobserved heterogeneity. What do I mean by unobserved heterogeneity? Well, people with the same X values don't necessarily have the same rate or probability of the count outcomes. They differ. Even if they have the same X values, they differ because of unobserved variables that influence the log rate. And we put all of those unobserved in the residuals, just like we do in linear regression. Now here, negative binomial, that distribution is not normal. It's e to the power of epsilon has a gamma distribution. Gamma has to do with the chi-square distribution. So it's a little bit different. But as in the random intercept Poisson model, it accounts for unobserved heterogeneity. If we're using then the so-called neg-bin2 parameterization, there's a very good book by Hilby on negative binomial regression, a whole book devoted to that. Hilby 2011, you have the reference in the book that we're talking about today, our book, There's also a very good book by Scott Long from 2007, which I recommend. So it has a mean of mu, as does the Poisson model, and the variance is mu times this expression. So you have one more parameter here now. So you have two parameters, and that is the so-called dispersion parameter. And the regular Poisson model is obtained when that dispersion parameter is 0, because then that term is 0. Variance becomes mu, the same as the mean, which was the limitation of the Poisson model. But having that alpha, particularly when it's greater than 0, the negative binomial gives much higher probability for low counts, just like zero inflated Poisson does, but without introducing a zero class. So it's not a mixture. Other count models treated in our book and in Hilby's book are zero inflated negbin. You can have a zero inflated negbin, binary count part like for zip. You can have a zero truncated count variable, zero probability for count equals 0. Certain applications call for that. And a hurdle model, which is what we will call two-part model today. We will not do a two-part count model, but we will do a two-part continuous model. And it's a binary model for being at 0 or not, combined with a zero truncated count model. That is, those are above 0, using then the zero truncated count part. And then you have varying exposure count models, which are dealt with in the book. Finally, how to compare these models? Well, all right, we're going to work in maximum likelihood settings now only. So in Mplus terms, we don't have the WLSMV, weighted least squares estimator. We don't have Bayes yet for counts, although that is in principle possible. We're going to work with Bayesian information criterion. Even though this says Bayes, it comes from maximum likelihood. It's called BIC. And it works with the log likelihood and the number of parameters. The number of parameters is R here, not the count before, but it's a number of parameters, and it's the sample size. So you want to have a high likelihood, but you can get a high likelihood, which is a good fit to the data. You can get that trivially by just increasing the number of parameters. So you have to have a penalty for increasing the number of parameters. So that's why you have two terms balancing each other. So as it says here, a model with we want low BIC. And the way we're scaling things, low BIC is good. Some other software, high BIC is good. But for us, low BIC is good. Lower BIC is a better model in terms of balancing the fit of the model, which has to do with the log likelihood, and model parsimony, that is having few parameters R. And we multiply the R by the log of the sample size for theoretical reasons. But anyway, that's the penalty part of it. So BIC is going to be used to compare a series of models here. And with that, I'm handing over to the other speaker.